In this video, we are going to be continuing with the differentiation of functions. And today we will be covering the logarithmic and exponential functions. Later on, we'll start to cover some more complex functions such as the hyperbolic trig functions or the inverse trig functions. And then we'll move away from functions as a whole and start talking about how to differentiate graphs like circles and ellipses. Alright, let's get started with defining and differentiating the natural exponential function. Now I'm sure many of you will recognize this from pre-calculus. This is the natural exponential e to the x. And e to the x is how we can define a lot of different interest and exponential decay problems, which is helpful for us. And it was definitely helpful in pre-calculus. But now we're really going to do a deep dive into the number e itself and why it's so important in the world of calculus. So we can define e with a limit. So we can say the limit as h approaches 0 of e to the h minus 1 over h is equal to 1. But what I find really interesting is how we can differentiate the exponential function. The derivative of e to the x is just e to the x. That's it. It's super simple. So e to the x is its own derivative. So if I want to find the slope at a point x, I can just plug it into e to the x and there's my slope. It's super easy. That's why we love e to the x in calculus. It's going to be really nice for basically our entire single variable calculus course. Alright, so now let's expand to the general exponential. So let's say I have a function b to the x and I want to take the derivative of that. We can use some logarithmic properties and some exponential properties to rewrite this as e to the ln of b times x times the derivative of the natural log of b times x. And we can continue to rewrite this and we will get that the derivative of b to the x, our general exponential, is equal to b to the x times the natural logarithm of b. So that's how we are going to expand to our general exponentials, the general exponentials. Alright, let's move on to some logarithms. So let's talk about the natural logarithm first. So if I want to differentiate the natural logarithm, I'm just going to get 1 over x. There we go. And that's also super simple. Not as simple as e to the x, but still we can work with that. And when we take the derivative of our natural logarithm and we put a function inside, the chain rule is really nice. And it means that the derivative is just going to be 1 over our function u times the derivative of our function u. So we can actually usually just rewrite this as u prime over u. Or, if you're more a fan of the function notation, g prime of x over g of x. Alright, so we did the natural logarithm, and that's all well and good. Let's move on to the rest of the logarithms with bases. So if I want to take the derivative of a logarithm with a base of b of x, then our derivative will be 1 over x times the natural logarithm of our base b. Alright, so now that we've got all the theory covered, let's do some examples. So we are going to take the derivative of x times the natural logarithm of x minus x. Alright, so immediately we can see here that we are going to need to use the product rule. And we have a product of two functions, so f of x will be x and g of x will be ln x. If we plug this into our formula, we are going to get the derivative of x times the natural logarithm of x plus x times the derivative of the natural logarithm of x. Now, I should mention we're only dealing with this set of terms here right now, and we will deal with this one later on. Alright, so if I have that derivative, I can just finish the job by simplifying, and then we're going to add the second term, and that's going to give us the natural logarithm of x minus 1 plus 1, which is just the natural logarithm of x because these two cancel out. Alright, let's do another example. So we're going to take the derivative of e to the negative 2x. Alright, so we need to apply the chain rule here. So what I can do is I can set u equal to negative 2x, then f of u will be e to the u. That means f prime of u will be equal to e to the u, and then f prime of g of x will be e to the negative 2x. All right, that may have seemed super simple, but it's important that we get it down. And then if we're going to take the derivative of our inside function, that's obviously just going to be negative 2. So then we bring that out to the front. So that will give us negative 2e to the negative 2x. All right, let's do another example. So we are going to take the derivative of x to the root x. And we can rewrite this with some logarithmic maneuvering to get the derivative of the square root of x times the natural logarithm of x. And now we can just apply the product rule here, and we will get the square root of x times 1 over x plus ln x times 1 over 2 root x, with 1 over x being the derivative of our natural logarithm and 1 over 2 root x being the derivative of square root x. All right, now we can just do some algebra, and we will get that our derivative is equal to x to the root x times 2 plus ln x over 2 root x. And that is our third example. Let's do another. We're going to take the derivative of the natural logarithm of the sine of x. So again, we're going to use the chain rule here. So we're going to set u equal to sine of x. That means f of u will be ln of u. That means that our derivative of u will be 1 over u. And then f prime of g of x will be 1 over sine x. Great. Now, what we need to do is we just need to take the derivative of sine of x and multiply it by our f prime of g of x. That will give us 1 over the sine of x times the cosine of x. And if we simplify this, we will just be given with the cotangent of x. And that is due to some of our trigonometric properties that we can apply here. All right, let's do another example. We are going to take the derivative of the log base 10 of 1 plus cosine of x. So we need to apply the chain rule, and we are going to need to use our logarithmic differentiating skills. All right, so that will give us 1 over 1 plus the cosine of x times ln of 10, because we're taking the natural logarithm of our base, and then times the negative sine of x. That gives us the negative sine of x over 1 plus cosine x ln of 10. And that is the end of our fifth example, and we will be ending it here for logarithmic and exponential differentiation. I hope this was helpful and build it on some of the ideas that we talked about earlier. Next time we will be back to talk about some of the hyperbolic trig functions. Then we'll be moving on to implicit differentiation to talk about differentiating implicit curves. All right, we will see you guys later. Thank you so much for watching. Please like and subscribe. Bye-bye.